What is up, bro? I hope you're learning from this failed idea series a lot. So, when we first learned about this second law of thermodynamics, we all had this inner demon to just invent something that breaks the law of conservation of energy, that breaks the second law of thermodynamics. We all tried to build a kind of perpetual machine that just creates infinite energy loop. So, this was my try for creating a perpetual heat engine model. So let's take a look at it. So this is the apparatus. Let me first explain it a bit. As you can see here, the apparatus consists of this container that contains n moles of ideal gas. The container's walls are adiabatic. Let's assume that everything is ideal and we are just working with ideal conditions, ideal environment, and ideal gas. So there is this container here, and in this container we have filled n moles of ideal gas, and there is a piston above it. The wall of this container is made up of adiabatic material. If you don't know what adiabatic is, it is a kind of material that prevents heat exchange between environment and the system. So adiabatic ensures that there is no heat exchange between the system and the surroundings. Now, here we have a small window that can be opened up to expose this isothermal layer of a ball. Now, note that there would be no exchange of mass or gases between the surroundings and system. The only exchange that would happen is when I open the windows, and this isothermal layer will be exposed, and then the heat from the surroundings can come inside the system and just do what heat does, make other things hot. And there is this thermometer, two thermometers actually, to measure the temperature of inner system and the outer system or outer surroundings. So this is the apparatus, and this is an ideas file. I actually have a lot of ideas that I write in this file. So let's take a look at the mechanism then. So let me explain you the mechanism in this way. What happens is that initially what happens is that the adiabatic wall is completely closed. So that window is closed as well, and there is n moles of ideal gas. Just assume that initially the gas is cold and the temperature outside in the surroundings is hot relatively, and the piston is just staying here. It is frictionless, assuming ideal conditions. Now, the way to start the process is first I fix the piston in its place so that there is no work done, the piston doesn't move. Then after that I open this adiabatic window and the heat starts to exchange between the surroundings and the system. So this causes, now note that I have fixed the piston in place, so there can be no increase in volume of the gas. So what would happen is the temperature, note that initially the temperature of the gas is cold and the surroundings is hot. So heat will travel, heat will conduct from outside surroundings to the system, and because there can be no work done or increase in volume, it would be an isochoric process. So the pressure and temperature of the system would increase, and I have these two thermometers here. So I let this process continue, this process of heat exchange and increase in temperature and pressure, until the temperature of the inner and outer surroundings and system becomes equal, which I can check from my thermometers. And once that happens, what I do is I close the windows. So now the whole system is adiabatic and there can be no exchange of heat between surroundings and system. So it is a completely contained system. The heat is contained inside the system, it cannot flow out. So now I so now let's note what has happened is the pressure inside the system of the pressure of the gas has increased a lot, and the temperature has increased, but the temperature has become equal to the surroundings. And now I remove this initial pressure from the piston, or I unfix the piston was initially fixed and I make it free now, so it is open to move. So now what has happened is the pressure inside the system is greater than the pressure outside, which is just 1 atmospheric pressure, 1 atm, and the inside pressure is much larger, which honestly depends on the initial temperature conditions of the system and surroundings, but you get my point. So now the pressure is high inside this gas and the pressure is lower here, and this is free to move. So because of the pressure, gas will push this piston outwards, and because there is no way for the heat to exchange, it would be an adiabatic process. And in adiabatic process, what happens is the volume increases and the pressure and temperature decreases. So this happens, the pressure decreases until the pressure inside the gas, inside the system, becomes equal to the outside pressure. So both become 1 atm. And once that happens, now I can intuitively say that because the pressure has become equal, now the volume has increased, obviously because the piston has moved up, and the temperature has decreased. Or I can say the gas has become cold again. So the initial conditions have been kind of restored, but with a twist that the volume has increased. And that volume increase or that work done came from the heat that was provided to my system by the outer surroundings. So that heat from the outer surroundings is converted into the work done or increase in volume of the system. And now I have kind of achieved that initial conditions again. So the temperature of the system is again cold, the gas is cold, and I can repeat the same process again. I can just open the windows again, fix the piston, and start it all over again and again. And I thought this process is perpetual. Honestly, you have to like fix the piston. It is manual, but it is perpetual. You can find a way to automate it. It's not that hard. So this was the diagram, the graphical interpretation of my heat engine model. It is like first pressure is P naught, so say, then there is this isochoric increase in pressure, and then adiabatic increase in volume, and the pressure decreases and it achieves this kind of initial condition, and this same process goes again and again. And this area under this triangular curve is the work done by the heat engine. And once I drew it, I thought where could actually use it. So I had this idea that this can actually be used as a kind of air cooling system. Now obviously it wouldn't be as effective as some other air cooling systems like the AC or the cooler, but when we have a lot of heat produced in the surroundings, for example in case of say other engines like motor engines or in the silencers of our motorcycles, the gas released is very hot, which makes the surrounding very hot. So I can use this model to kind of cool down my silencer. It kind of converts heat into work very efficiently, so it can be used as a coolant. And this is the mathematical formulation. So I sat down finally. I didn't waste so much time on it like the Newton's law, and part of the reason was because I was introduced to this laws of thermodynamics quite recently, and I was giving JEE exam as well, so it was relatively easier for me to derive these formulas. So here you can see initial is V0, P0, T1. You can read it yourself if you can. I'm not going to explain it in detail. So now when I derived the formulas, I found out that it's not actually as perpetual as I thought it was. It is not like 100% energy efficient. So I thought the diagram would look like this. So there would be a constant increase and decrease of pressure and volume, but that is not the case. What actually happens is the first triangle is quite bigger, then the smaller one gets, then the next one gets quite smaller, and so on. And this kind of achieves like a stability at some point of time. So it isn't a perpetual heat engine. Or you can say that after one process, it's not that the initial conditions have been achieved. Or suppose I was initially starting with the temperature of the cold gas as 20 degrees Celsius and the outer surroundings was say 60 degrees Celsius. So now once that isochoric and adiabatic process has happened, now the temperature has decreased for sure, but it wouldn't be like my initial temperature of 20 degrees Celsius. It would be maybe 30 or 25 degrees Celsius. It wouldn't be 20. So my initial conditions are not reached. And this keeps on stacking up as a domino effect. And I also didn't push as hard on making this heat engine model because I don't know where this could be used, because the work that is being done is just increasing the volume or just pushing the piston in one direction. I wonder where that could be used. Maybe in some cases where we don't need oscillatory motion like normal heat engines. Maybe somewhere if we need just a one unidirectional heat engine that the piston just moves in one direction constantly, it keeps on expanding, then yeah, maybe we might use it, but I don't know. So yeah, this was it. And yes, I also have this thought that what essentially I am doing is I'm combining isochoric, I wrote isothermic here. So essentially what I'm doing is I'm combining isochoric and adiabatic expansion. So I'm not sure if the work done is greater or the heat absorption is greater in this case in my heat engine model, or in another case where I don't do this advanced kind of shit and just pour a cold gas in there so that it just normally expands, it isothermally expands. Would that do more work done, or my model? Which is more efficient? I don't know. There is work to be done, and if I found out that this my model is more efficient than just pouring a hot gas into the system, then yeah, I could make a kind of a coolant engine and can be used as a business idea. Don't steal it. I'll sue you. So yeah, this was it for the video, bro. I hope you enjoyed it. It was kind of fun for me to think of this perpetual heat engine model. It was kind of a new idea, and I'm really proud of it. Keep thinking, keep having fun.